Okay, we're gonna talk about how we would integrate some function. In this case, sigma of xy is two xy, maybe it's a mass density function to get the total mass of this thing. Maybe it's something else, maybe it's a charge density, for those of you who are dealing with those in physics, okay? So what I want to do is I want to partition either x or y. I could do either. And well, I'm going to partition the x interval from -3 to 3. Is it? And we have our typical intervals. Xi minus 1 to xi. Well, that's and for every x interval. We've got a chunk of this stuff. It's not a rectangle anymore. But if the partition is fine enough, if the n is a big enough number, these things will, as n gets bigger and bigger, these things more and more closely approximate the actual. Curve. So what we're going to say is we're going to say, okay, well, we're going to make these into rectangles and something like this. In some way or another. So that we can partition the y. So the typical interval, let's just say that this is the interval. Xi minus 1 xi. So we're going to enlarge that interval. And there's an xi star in here somewhere. And it's an xi star that we're going to evaluate. This is your curve up here. At xi star. We just cut this thing off, make it a rectangle. Again, if n is big enough, if the interval, the delta xi is small enough, it's not going to make much difference before I cut this thing off. Because there's not going to be very much difference between how high the rectangle is here and how high it is here. As n approaches infinity and the mesh of your partition approaches 0, those discrepancies disappear. All right, you want to understand that. Okay, so now I want to partition my y. Typical increment gives us this. Partition y from y equals what? y equals what? So think about it for a second, see if you can tell me what the limits on y ought to be. Okay, not sure, I was recording. Want to integrate this over this half circle, actually. Yeah, so if this is a repeat, go ahead and listen again, or just get through it. I want to integrate this over the half circle here. So what we do is we partition our x interval from -3 to 3. We could partition the y interval from 0 to 3. That would be equally valid. It would work. But we're going to partition the x interval. You're a little more used to looking at it this way. So here's our partition. -3 to 3, x0 equals 0, -3, xn equals 3. We have our typical interval xi minus 1 to xi here, and that's what we want to look at. So let's just say that's the interval xi minus 1 to xi right here. So now we're looking at this slicing. And so we'll partition every slice, but we're just going to indicate the partition of this slice. And this could be any slice. Okay, so enlarging that increment and distorting it a good bit. We have xi minus 1 here, xi here, and an xi star in the middle. So this is our typical x increment. We want to partition y within the x increment. From y equals what to y equals what? What's y down here? What's y up here? Okay. So make sure we're in focus. Make sure we can see the whole board. Okay. Well, pretty clear that down here, well, that corresponds to the point here. What's y? It's 0. It's on the x-axis. Okay, so we go from y equals 0 to y equals what? Well, the y equals what can be a little bit problematic until you see it, and then it becomes non-problematic. Okay. Well, y is going to go up to here. Okay. Well, y is going to go up to here. Where's here? Well, it's here. And if you draw this line here, and this line here, then complete the triangle. What are the dimensions of this triangle? Well, from here to here is xi star. Here, so yeah, we've got this. Then the triangle goes back to the origin. Okay. And I'm not going to draw here because the whole thing is distorted like it is. Okay, and we got 3 here. So what we have is the square root of 9 minus xi star squared. Okay, so y goes from 0 to square root of 9 minus xi star squared. So what's our partition? I have room to write it. Okay, I'm going to call this y sub m sub I. And that's gonna be 9 minus xi star squared. Square root of 9 minus xi star squared. So y is partitioned from 0 to here, from here to here. So we form the sum. Actually, I was gonna do total area, but I'm not asking for total area, I'm asking for mass. Whatever, okay. Or integrate 2xy. So. Typical increment. The product of delta sigma of xy, delta xi, delta yj. Well, that's going to be the thing you're integrating times the area. If you think of mass density, it's the mass density times the area. But it's going to be at an x. Well, I'll leave myself reading those certain things. Okay. I can check subscripts. So we can write the thing we're integrating times the area. And we evaluate this at a sample point xi star yj star. And your typical increment. Looks like this. Now there's a point here. And I didn't leave myself reading the label. I'll have to write the label way down here and draw a long arrow. That's a point xi star yj star. Not necessarily in the middle of the increment, although I kind of drew it that way. It's at any point within this rectangular increment. Total of our sigma times area. Is a sum from I equals 1 to m, j equals 1 to m sub I. Delta xi, delta yj. And this approaches the interval. Now, the integral from what to what? Well, I goes from 1 to m, right? And that corresponds to x going from what to what? X goes from -3 to 3. So it's from -3 to 3. And that's of the integral. It corresponds to a sum from j equal 1 to m sub I. For every x, y goes from sum j equals 1 to m sub I. You have a different partition of y for every x. The partition goes from what? Goes from y equals 0 to the square root of 9 minus xi squared. So this would be then from 0 to the square root of 9 minus x squared of sigma of xi, yj. Well, that's 2xy. And then dy dx. Again, the y integral is inside the x integral because of the way we did our partition. We could partition x, y from 0 to 3. Your typical y increment would then go from negative square root of 9 minus y squared to positive square root of 9 minus y squared. We'll write that out. But we did done it with cross sections in this direction. So if you give me a y value, x goes from here to here. This is square root of 9 minus y squared, negative square root of 9 minus y squared. This is square root of 9 minus y squared, just by the same geometry that we used here. We just use the Pythagorean theorem. It's easy. Okay, well, of course, you got to do that anyway. Turns out this is not a difficult integral. So let's go ahead and evaluate it. Okay, we integrate this with respect to y. That's going to give us just 2x times y squared over 2, and that's just going to be xy squared. Evaluated from 0 to the square root of 9 minus x squared. That's then the integral from -3 to 3 of x times squared out detail square root of 9 minus x squared minus 0 squared with respect to x. Everybody understand everything that I just did? I'm just substituting this and this, and it's some standard integration. And then the algebra is really simple, so I'll kind of cut through it. You're going to get 9 minus x squared here, and then you're going to multiply that by x. You get 9x minus x cubed with respect to x. And I'm not going to take up valuable time to do that. So, okay. Now, if we wanted to get the area of this thing, what would we do? Well, we'd leave out the sigma of x, sigma xy. We just do the integral of the area increments. Okay. Well, let's look at that. Okay. What's the area? That's just the integral from -3 to 3. There's the integral from 0 to the square root of 9 minus x squared dy dx. Well, antiderivative of dy is just y. It's antiderivative of 1 dy if you wish. And that's going to give you the square root of 9 minus x squared. Now, how do we integrate square root of 9 minus x squared dx? So we're going to do u substitution. We want to use cosine theta or sine theta, it doesn't matter. So there's our u substitution. It's 3 cosine theta, and it's negative 3 sine theta. I just want to put this out. We're going to factor 3 out. We're going to get a 3 cosine theta quantity squared. We factor a 9 out of this, it becomes a 3, and we end up with 1 minus cosine squared theta times negative 3 sine theta d theta, which is then going to give us negative 9 times the interval from negative 3. And since I've done the substitution, I want to say x equals negative 3 to x equals 3. Just so I don't think that theta goes from negative 3 to 3. And we'll figure out what to do when we get there, but this is going to give us negative 9 sine squared theta d theta. Okay. A couple of ways to do that. Sine squared can be expressed as in terms of sine or cosine of 2 theta. So that's perfectly legitimate. Now, I do have a problem here. Is, the problem is the negative sign, but got to be there. Okay. I don't have room. I'm going to do an integration by parts. Sine theta, u equals sine theta, v equals sine theta d theta. And there are a couple of steps we end up with a reduction formula. Okay. I'll let you do the integration technique, because that's not what we're trying to teach here. If I had room, I'd do it. But, we end up with 9 pi over 2. How do we, I know we end up with 9 pi over 2, because that's half the area of the circle of radius 3. Okay, so I know what the answer is. It's, how do we get from here to here? Okay. And there's some steps in here that I don't want to do later. You might need to review some integration technique. And there should be 2 methods for doing this. One is a trig formula that relates this to cosine of 2 theta. 1 minus cosine of 2 theta over 2 or something like that. Okay. And that can be derived easily if you know how to derive the basic sum of 2 and 1, difference 2 and the formula. The other strategy again is a couple of steps of integration by parts that lead to a reduction formula. You're going to end up with a theta over 2. And that's going to go from negative theta over 2 to positive theta over 2. We'd also do it in polar coordinates, which is much easier. And we're going to see that. Okay. The essence and the thing I really want you to see is what happens in the partitioning process. So that we know what limits to put on our interval. Partitioning process, you partition one of your variables over the appropriate interval. And then you partition the other one over the typical increment in the partition of the variable you started with. You don't say y goes from 0 to 3. That would give you a rectangle, as you know. Okay. Well, it goes from 0 to 3 if you're here. If you're out here at x star, y goes from 0 to square to y minus x star squared. Okay, well, same idea. Be applied. Now, this is very well drawn. It ceases to be a function right here because it doesn't satisfy the vertical line test. Let's make this kind of come down here. Maybe it's a bird. Okay. And, you know, it kind of gets retrograde here, but I'm not going to change it. Okay. Here's a solution of f of x equals b of x. And here's another solution. Call this solution A. Call this solution B. Okay, so this is a line x equals A, and this would be the line x equals B. How do we deal with this? We think, okay, we partition. The x interval A, B. Now, if I give you two functions, you're going to have to find the points where they meet. Gotta get more complicated than that, but that's the general idea. Okay, partition the x interval from A to B. What goes from point to what? So we write out all the details, but we partition the x interval. And right here is what we get from typical interval, right? So the ith x increment, call that the ith x increment. Y goes from what to what? You can write it down. Well, y goes from here to here. Well, what's the y value here? Not really. We got a pretty good answer. And what's y down here and what's y up here? Well, you're on the graph of y equals g of x. Pretty obviously, y ought to be a point on the g of x graph. Or value of the g of x. So I'm going to say g of x to f of x. That's not specific enough, but that's the idea. Now, how can I be more specific? Because remember, we've partitioned the x interval from A to B. Oh, was I recording that when I explained all that? Go ahead and do it. I'll explain it again. I'm pretty sure we got this recorded. Anyhow, we got two curves. The f of x curve is here and the g of x curve here. We go from the intersection, one intersection of the curves to the other. Okay, and we want to integrate to find this area. So we partition the x interval from A to B. And on the ith x increment, put our limits on y. Well, the ith increment has xi minus 1 here, xi here, xi star here. On this, which represents this strip, which represents the ith x increment, and the region of the, well, the strip of the region that corresponds to that increment, y goes from here to here. What's this y value? What's this y value? Well, we're modeling everything within the strip in terms of xi star. So down here, we're on the g of x curve. This point would have y coordinate g of xi star. This is on the f of x curve. This would have y value g f of xi star. Okay. So our partition of the region is pretty simple. Typical partition for x from A to B, x naught equal A, x naught equals B, and the usual stuff in between with the typical increment. And then y goes from y naught equals g of xi star, that's the y down here, up to f of xi star, which is the y we have up here. And there we have it. If we're doing the integral, we just sum up the delta x times delta y, x running from I to m, and y from j to m sub I, the different limit on y for every I, for every x increment. And this approaches the integral from A to B of the integral from g of x to f of x y dx. That's pretty straightforward. And then, of course, the integral from g of x to f of x with respect to y is just f of x minus g of x dx. Now, if we had some other function in here, if we had a density and we're trying to find a mass or a charge density, we're trying to find a charge or some other quantity that we want to integrate over this area. Then we would insert it here, and what we get here wouldn't be as simple as what we have. So what I've asked everybody to do now is try this. If f of x is x squared, g of x is 2x plus 1. Just do the whole process. See what your integral is. Okay. So we're going to do the thing we did here. For f of x equals x squared, g of x equals 2x plus 1. First thing I would do is I would graph both of these functions. And if you need a graphing calculator to graph them, you really need to know your functions better. But let's take that. X squared graph looks like this. 2x plus 1, slope of 2 goes through the point 0, 1. And out here someplace, it intersects the parabola. Okay. So. Better have two intersection points. Otherwise, you don't have an A and a B. Okay. Two intersection points, x squared equals 2x plus 1. That's x squared minus 2x minus 1 equals 0. X equals 1 plus or minus square root of. Okay. Now, if you plug into the quadratic formula, I mean, you get literally negative of -2 plus or minus the square root of -2 squared minus 4 times 1 times 1 times -1 over 2. That equals 1 plus or minus the square root of 8 over 2. You factor of 4, 8's 4 times 2, square root of 4 times the square root of 2 is 2 times the square root of 2, divide by 2, and 1 plus 2 square root of 2 over 2. Okay, you can't read what I wrote anyway, but if you just do the Pythagorean theorem, quadratic formula. You got it. So now we have the interval from 1 minus the square root of 2 to 1 plus the square root of 2 of the integral from x squared, because it's lower, to 2x plus 1 dy dx. And that becomes very straightforward. Go ahead and do it quickly. Okay, this integral is just y evaluated between here and here. It's going to be this minus this. There it is. I'm having trouble seeing that that's going to end up positive. The x squared is definitely lower. I mean, y-intercept of this is at 1. Y-intercept of this is at 0. And I've got a suggestion here. Somebody's saying something that I skipped over. Okay, I changed the sign. It is 2x plus 1 because of what I just said, obviously. And if it's 2x minus 1, then the intercept is down here. And then you got problems. Because I don't think it intersects at all. Anyhow, okay, 2x plus 1, 2x plus 1, that'll make this plus. And then you evaluate it. Okay. And it's not worth my time to do that. Use a binomial expansion. It's easy to cube this. Okay. would be 1 plus 3 squared or 2 plus 6 plus 2 squared 2. That over 3. A little dubious, but I guess it ends up positive. It has to, that area is positive. Okay. Okay, now your book talks about type 1 and type 2 regions. I'm going to let you read about that rather than try to explain it. I want to give you a little heads up on polar coordinates. Oh, yeah, another thing that I meant to mention when we were back wherever we were before we were here. Another interpretation of this 2xy integral of 2xy is a volume z equals 2xy, and you're integrating the value of z over this circle, which means that you've got this surface above or below the circle. Thinking when you get done integrating this, you might get 0. Because 2xy is symmetric with respect to the y-axis. It's above the y-axis on this side, below on this side with equal and opposite values. So if you did that as a surface, you'd have an equal volume on this side and this side, but this would be negative. Okay. So just be aware, your book will show you examples that this could be a density increment, a density integral, although you'd have negative densities on this thing. So density probably is a good model. Okay. But you can have a surface, let z equal this, and you get a surface above or below this region. So you get volumes. Oh, we're out of time. I was going to do a little polar coordinates. Let's look at the clock. Okay, so we'll look at polar coordinates. I recommend always that you read the section before you come in here. Get your brain working on it, whether you understand it or not. Okay, and you're going to understand most of it anyhow.